Hi everyone, in this video we are gonna study about electric dipole. So electric dipole is an arrangement of two equal and opposite charges which are separated by a fixed distance. So let's say there are two charges, a minus q charge and a plus q charge, and distance between these two charges is fixed, and that distance is, let's say, 2a. So we define dipole moment for an electric dipole as follows. So dipole moment is a vector quantity denoted by p vector, and the magnitude of this vector is basically distance between the negative and positive charge, which is 2a, multiplied by the magnitude of the negative or the positive charge. So basically the magnitude of this vector is 2aq, and direction of this vector is from negative charge to positive charge. So basically p vector is this vector whose magnitude is 2aq and direction is from negative charge towards the positive charge. So there is a derivation that can come in CBSE exams, is that you are given an electric dipole and you have to find the field due to this electric dipole at some point on the axis, on the dipole axis. So let's say this point, let's say we choose this point to be the origin, which is the center of the line joining the negative and the positive charge. Let's mark that point as origin, and let's assume that the distance between these two charges is 2a, which implies this distance is also a and this distance is also a. And let's try to find electric field intensity at any point which is at a distance of x from the origin. So let's try to find the electric field. So we'll first find the electric field due to negative charge, and since negative charge would attract +1 coulomb test charge placed here, so electric field due to negative charge E1 would be in left direction, and since positive charge would repel this +1 coulomb charge, electric field due to positive charge would be in the right direction. And since the magnitude of the charges is same, which means the charge which is closer to this point, let's say this point is marked as A, so the charge which is closer to point marked A, which is this positive q charge, will have higher electric field. Basically it will exert higher amount of force because of Coulomb's law, kq by a square, because q for both the cases is same, and whichever has the smaller distance a or distance between the two charges will exert higher force. So this q will exert higher force, which implies E2 would be greater than E1. The magnitude E2 would be greater than E1, and net field would be in the right direction, which would be equal to E2 minus E1. So we have to find this E net. So let's try to quickly find this. So E1 is nothing but E1 is equal to kq by, so this distance is a, kq by a plus x square, and E2 is kq by, so basically you have to subtract a from x minus a square, so you have to subtract this length to get the distance between from here to here, which is x minus a. So now we calculate E2 minus E1, which is, let's take kq common, 1 upon x minus a square minus 1 upon x plus a square, which is equal to, so x square plus a square plus 2ax minus x square plus a square minus 2ax divided by x minus a whole square into x plus a whole square times k cube. So the numerator would be simply 4ax k cube 4ax by denominator would be x square minus a square whole square, because x minus a into x plus a is x square minus a square. Now we know that the direction of E net is in the same direction as our P vector. So we can write this E net as follows. So the magnitude is of P vector is 2aq. So magnitude of P vector is 2aq and direction is from negative to positive charge, which is same as direction of E net. So we can replace 2aq with P. So it would be 2p x upon x square minus a square whole square times k. So this would be E net, and this is also a vector which has the, so this E net has same direction as the P vector, and magnitude of E net can be obtained by replacing the magnitude of P vector. So magnitude of P vector is basically 2aq, so which will give us the original thing, the magnitude which we calculated. So this is just an easier way to denote E net. So one thing is to note when x is very large than a, so basically we can ignore a in the denominator, then this E becomes k times 2p by x cube, which is equal to 2p upon 4 pi epsilon naught x cube. So it is advised that you remember this formula, because sometimes there can be equations in mains where you can directly apply this formula. And similarly, you have to calculate the electric field due to this dipole. So another question that might come in CBSE is that you have to find this electric field due to the dipole at a point not on the x-axis but on the y-axis. If this is the origin, so this is called as equator or equatorial axis. So you have to find electric field at any point here. So let's say the distance from origin is again x, and we know that this is a, this is also a. So we know that negative charge will attract positive charge, so direction due to negative charge would be in this direction, direction due to positive charge would be in this direction. So this would be E, this would be also, let's say this is E naught, this would be also E naught, where E naught's value is kq by this direction, a square plus x square, this length, which is same for both, kq by a square plus x square. So basically kq by r whole square, where r is root of a square plus x square, so which is simply kq by a square plus x square. And let's say this angle is theta, which implies this angle is theta, this angle is theta. So net electric field net would be in left direction, because y components will cancel out and x components will add up. X components would be E naught cos theta plus E naught cos theta, which is equal to 2 times E naught cos theta, and cos theta is base upon hypotenuse, so cos theta is base upon hypotenuse, and 2 times E naught, so replace E naught from above, kq by a square plus x square. So this would give us E net to be 2aq k times a square plus x square raised to power 3 by 2. So we can see that the direction of E net is opposite to the direction of P vector, and the magnitude of P vector is 2aq. So we can replace this 2aq by magnitude of P vector, and so E vector can be simply written as minus k times P vector by a square plus x square raised to power 3 by 2. And if a can be ignored, basically distance from the origin is very large, in that case our E vector is simply minus k P vector by x cube, which is equal to minus k upon, so basically which would be equal to minus p upon 4 pi epsilon naught x cube. So I would again say that remember this, because it can be used in directly in some questions. So things to remember: are as follows. So electric field is equal to 2p upon 4 pi epsilon naught x cube on the axis, and minus p upon 4 pi epsilon naught x cube on the equator. So basically on the equator it's in opposite direction of the electric dipole, the field is in opposite direction of electric dipole, and on the axis the field is in the same direction of electric dipole moment. So now so this is kind of something that can be asked in like mostly advanced, might be asked in one of the difficult question in mains, but it's kind of an advanced concept. So basically now you have to do is like, given an electric dipole and given a point x, let's say, which is like very far. So x is, we are assuming we are calculating this only for x greater than a. So given a point, so this is an electric dipole placed here with dipole moment p. Okay, so we have to find the electric field at an arbitrary point which is not on the x-axis or the y-axis, but makes an angle theta with the x-axis, let's say. So we have to find the electric dipole at this point, and using the formulas that we just derived for electric dipole at equator and axis, we can easily find this. So let's say this distance is x from the origin and this point is origin. So we can create components of this dipole moment, and we can simply treat it as a vector. So this dipole moment has two components. So this component would be p cos theta, and this component would be p sin theta. So now this point for this component p cos theta is just like another point on the axis. So the force due to axis is 2 times p cos theta by 4 pi epsilon naught x cube. And p sin theta, for p sin theta, this point is just like a point on the equator. So for the equator, the force would be in opposite direction and magnitude would be p sin theta by 4 pi epsilon naught x cube. So basically instead of p, we will use p sin theta in the formula, and instead of 2p, we will use 2p cos theta in the formula of the axis and equator. And then we can easily calculate the resultant. Resultant is basically, we will take p upon 4 pi epsilon naught x cube common, and inside it we will be sin square theta plus 4 cos square theta root. So basically resultant is simply the x coordinate square plus y coordinate square ka under root, and this is nothing but p upon 4 pi epsilon naught x cube 1 plus 3 cos square theta, where value of p is 2aq. If you are given the value of dipole moment directly, then you can use that. Otherwise, if you are given a and q, you can use 2aq. P is equal to 2aq. So this is the magnitude of the electric field, and let's say direction of the electric field is somewhere here, the net direction, and it makes an angle of alpha. Then we can easily find that tan alpha is equal to p sine theta upon 2p cos theta, which would be equal to basically y component, which is this, divided by x component, which is this. So this would be simply equal to tan theta by 2. So alpha would be tan inverse tan theta by 2. So this, using the formula for the equator and axis of a dipole moment, you can easily calculate dipole moment at any point. That's why I said that it is very important to remember these formulas. So now let's study about force. So we have so far studied about force exerted by dipole moment on 1 coulomb charge. Basically we found the electric field of the dipole moment. Now we will find the force exerted on dipole moment. So instead of by, we'll study force exerted on dipole moment in a uniform, not dipole moment, basically dipole. Dipole moment is a vector quantity. Sorry, force exerted on dipole in a uniform electric field. So let's say the dipole is like this with distance of 2a, and it is kept in a horizontal position as shown in the figure. This is origin, and it's lying in a region with uniform electric field towards the positive x-axis, and the magnitude of electric field is capital E. So the positive charge experience a force in the direction of electric field, because that's how electric field is defined. Basically force experienced by a positive charge, 1 coulomb charge. So if 1 coulomb charge experience a force of E, Q would experience a force of QE in the direction of electric field, and negative Q would experience a force of QE in opposite direction of electric field. So if we make FBD free body diagram of the dipole, let's say this is dipole, so basically this is dipole in this free body diagram. So a force of QE is exerted to the right, a force of QE is exerted to the left, therefore force net exerted on the dipole is 0. And this position is known as stable equilibrium, because if we shift the dipole slightly, let's say we rotate the dipole slightly, so the dipole becomes like this. This is Q and this is minus Q. Then if we shift it like this and we keep it, it will automatically come back to its original position. That's why it is known as stable equilibrium. So first of all, you have to understand that this position is an equilibrium position, because in this position the net force is 0 and net torque is 0. So you can calculate torque at any point. Let's say you calculate torque at point origin, then you can clearly see that, so torque is given by force into perpendicular distance of the force. So force is QE and the perpendicular distance of QE from origin is 0. That's why torque in this position is 0. But let's say if we shift it slightly like this, and this is origin, in this position so in this position number 1, net force is 0 and net torque is 0, and we call it to be in stable equilibrium. So now let's see for position number 2. So here in this case, so in this position net force is 0, because right hand force is equal to left hand force, so force net is 0, but net torque is not 0. Why? Let's say this angle is theta, angle with the horizontal. So if this angle is theta, this angle is also theta. So we can see that, let's calculate torque at origin. So this distance is a, therefore this distance is a sine theta. Similarly, this distance is also a sine theta. So torque due to this force at origin is QE a sine theta, and it's in the clockwise direction. Similarly, torque due to this force is also QE into a sine theta, which is force into perpendicular distance from the origin, which is a sine theta, and it's also in clockwise direction. Therefore torque net is 2QE sine theta. 2QE a sine theta. Now we know that 2AQ is nothing but magnitude of dipole moment, which is P. So we can write it as P sine theta. And we know that P sine theta is equal to magnitude of vector. So this is P vector, direction of P vector. And so this is direction of P vector, and this is direction of E vector in this case. So we are assuming that E is horizontally and uniform. So the direction of torque, so torque is also a vector, and direction of torque is downwards, which is same as, so direction of torque is downwards, which is into the plane, and it is same as P cross E, and magnitude of torque is also same as P cross E. So magnitude of torque is equal to magnitude of P cross E. So an angle between P and E is theta, so which will be equal to P sine theta. So in a uniform electric field, if it is not in if the dipole is not in an equilibrium position, it experiences a torque of P cross E. Now let's say in the third position, so let's say the positive charge is here, we have completely rotated that dipole, and my negative charge is here. Here this Q will experience a charge towards the left, and this negative Q would experience a charge towards the right, same as in the first case. So, and torque at origin is also 0, and force net is also 0. So force net is also 0 and torque net is also 0. So this is also an equilibrium position like the first case, but this is not stable equilibrium. By stable equilibrium we mean that if we shift it slightly like this, so if we shift it, it will completely rotate and come back to the position as in case 1. So it will come back to this position, minus Q here and Q here. It will not stay in the position, it will not stay in the initial position. In the first case it would stay in the initial position. Here it would change its position, it would completely rotate. That's why it's not stable. In first case it was a stable equilibrium. So this is the force and torque exerted on dipole in a uniform electric field. I hope it's clear. If it is not clear, please take your time, pause the video, and make sure that you completely understand this before moving further. And now finally we will calculate potential energy of a dipole. So we know that whenever we have to calculate the potential energy, we define a state, where we say that here the potential energy is 0, basically our reference state. So for the dipole we choose that reference state to be like this, when positive charge is like this and negative charge is like this. Basically the dipole vector P is making an angle of 90 degree with the x-axis. So at an angle of theta is equal to pi by 2, we call that dipole has a potential energy of 0, and this is by definition. Then we define the potential energy at point at an angle of theta for an electric dipole is as work done in changing position of dipole, basically rotating the dipole, or you can say rotating dipole from theta is equal to pi by 2 to any given general theta. Basically from angle pi by 2, rotate the dipole from angle pi by 2 to angle theta, and whatever work done is required for that in the rotation is known as potential energy. So let's say we rotate this dipole from 90 degrees to some angle theta. So the work done in this rotation would be the potential energy, and work done, for example, so work done is F dot ds, and similarly if it is a rotation, then work done is torque dot so if it is rotation, work done is torque into d theta. So, and we would integrate this, and we know that the magnitude of torque is P sine theta. You just saw that magnitude of torque is P sine theta. So we integrate this from theta is equal to pi by 2 to theta. So integration of sine theta is minus cos theta, and we take PE out. So this becomes PE times minus cos theta minus of cos pi by 2 is 0. So this is equal to minus PE cos theta. So this is potential energy at an angle theta. So we can see that potential energy at angle of 0 degrees is minus PE, negative potential energy. Potential energy at angle 90 degrees is 0. Potential energy at angle 180 degrees P, which is a positive potential energy. So basically in this position potential energy is 0. In this position potential energy is equal to minus P, which is a negative potential energy, and in this position potential energy is equal to P, which is a positive potential energy. So I hope this is clear to you. If you like this video, please subscribe to my channel and stay tuned. Thank you very much. Bye bye.